Today we're going to be talking about some basic rules for complex numbers and what they are. And we're going to start by investigating the function f of x equals x squared plus 1. So we've been working in quadratics and polynomials. This should be a very easy graph for us to sketch. This is the graph of x squared, shifted up 1 unit, so its vertex is at 0, 1. And this graph would open up. It's just a sketch, so I'm not going to get into plotting all of the normal integer points that I normally plot for that graph. So there's the graph, and then we've been solving polynomial inequalities. So if I want to solve this inequality, one is x squared plus 1 greater than or equal to 0. Because the zeros aren't easy to solve for, I should think about just the graph again. So I'm not going to sketch the graph again, but I'm going to make a note. Use this graph. Remember, when we say when is x squared plus 1 greater than or equal to 0, we can think of that graphically as when is this above or touching the x-axis? When is the graph above the x-axis? Now, the graph is never touching the x-axis, but it is always above the x-axis. So x squared plus 1 is always positive or always above the x-axis. All of these y values are positive. So if I were solving this inequality, x would be the set of all real numbers. Anything between negative infinity and infinity satisfies that inequality. If the inequality were less than 0, the answer would be no solution. And then getting to solving the equation of x squared plus 1 equals 0, we can see again from the graph that it never equals 0, so no solution for that. We could also try solving. This doesn't factor, but we've got the square root method. We could isolate x squared, square root both sides. So we get to x equals plus or minus the square root of negative 1. But we sort of run into a problem here with the real number system because this answer is not real. Remember, square roots really are saying what number multiplied by itself is equal to negative 1. And you can't, in the real number system, multiply any real number by itself to produce a negative value. You've got to have one negative multiplied by one positive to get a negative result. So instead of just stopping here and saying these problems are just not solvable, some mathematicians that we can thank have created an expanded number system using the imaginary unit. So the imaginary unit, which is lowercase I, was basically created to be able to solve equations like this. We don't want to have a bunch of problems where we just stop and can't simplify them or can't solve for x. We'll get to in the homework some practical applications of imaginary units as well. But basically, the imaginary unit I is defined to be the square root of negative 1. So not the plus or minus part, just the square root of negative 1. And then we can kind of build on that. We need to be able to simplify powers of I. So if I is the square root of negative 1, then I squared, if I square that square root, will be equal to negative 1. And again, these are imaginary units. So the reason we're allowed to just square and take away the square root, we're allowed to square something and get a negative, is because we're looking in the imaginary unit, this new number system. So this is just the rule that's been defined here. So if that's I, and that's I squared, then I to the third, if we want to simplify that in terms of I, so I don't want to have my answers in terms of square roots, so I want to leave them in terms of I to the third is just I times I squared, and that's just I times negative 1. So it simplifies to negative I. So as you're working with imaginary numbers, anytime you see I squared, you'll rewrite that as negative 1. Anytime you see I to the third, you'll rewrite that or simplify that to negative I. And anytime you see I to the fourth, you could say that's I to the third times I, or I squared times I squared, negative 1 times negative 1. I to the fourth simplifies to positive 1. So this little block, the first 4 powers of I, this is something you need to have memorized. Not necessarily the breakdown here, but you need to memorize the first 4 powers of I. So you should be able to know you've got I squared is -1, I cubed is -I to the 4th is 1. We'll expand about that. What about I to the 5th, 6th, 7th? We'll get to that in some of our examples. Okay, so that's all about the imaginary unit. What about complex numbers? So complex numbers are basically combinations of real numbers and imaginary numbers. Complex numbers are the big umbrella. So we've got complex numbers. Let's see. As far as the number system goes, complex numbers are on the top. And then within complex numbers, we have real numbers and we have imaginary numbers. So when I say find all of the complex numbers that solve this equation, I'm asking you for any real numbers and also any imaginary numbers that solve an equation. So if a and b are real numbers, then the number a plus bi is a complex number, and a plus bi is the standard form of that. So we call a the real part, write that first, and then we call the bi the imaginary part. And so a complex number can combine real parts and imaginary parts. Complex numbers, though, they could also just have the real part or just the imaginary part or some combination of both. So if b is equal to 0, then the expression a plus bi, if you plug 0 in for that, just becomes a. So it's possible that b is 0, and then you just have your complex number, a plus bi. Complex number is actually a real number. So complex number is the big umbrella. We're just saying if b equals 0, then you're falling into the real number category. If b is not equal to 0, then your complex number, a plus bi, would just be some combination of a plus bi. So the complex number, because it still has the I term in it, complex number is considered an imaginary number. All right, and then if a equals 0, so if there is no real part, if you just have a plus bi, but a equals 0, you would just be left with the bi part. And so in this case, this complex number, because all of these are complex numbers, this complex number is called a pure imaginary number. We're not really going to be quizzed on vocab as far as I can tell on the AP exam, but it's just kind of good to know that real numbers are complex numbers, pure imaginary numbers are complex numbers, and combinations of real and imaginary, so imaginary numbers in general, those are also complex numbers. For the rest of the school year, when we solve equations, we're going to be looking at all complex solutions. So not just real answers, but if answers contain I, we will give those as well. So what we're doing today is just kind of figuring out some of these rules. I know that you worked with complex numbers in Algebra 2, so I'm just reminding you of some of these rules just by example. So the directions are to simplify each expression. And what that means is write your complex number answers in standard form. So write them in the form a plus bi, real part first, imaginary second. And then if we're doing the math and we get powers of I larger than 1, we need to simplify those. And that's where we're going to come back to this idea. Where'd it go? This idea. We're going to simplify in terms of I. So I is okay. I squared, we're going to simplify to -1. I cubed, we will rewrite as -I. I to the 4th is 1, etc. So for our first problem, it looks like we've got 3 complex numbers. We're just adding and then subtracting. So with the addition, I can just drop these parentheses. Instead of plus -3, I'm going to write -3 minus 4i. I'm going to distribute the negative through the set of parentheses, so +3 plus 3i. We're trying to write answers in standard form, so let's look at the real parts first. -3 plus 3 cancels out, so I'm not going to write 0. I'm just going to simplify the i's. So 2i minus 4i is negative 2i, plus 3i is 1i. So this whole thing just simplifies down to I. And again, we want to leave our answers in terms of I, so I wouldn't say equals the square root of negative 1. Okay, number 2, we are squaring a binomial. Remember what that means. You can use the shortcut for squaring a binomial, or you can show yourself. This really means 3 plus 2i times itself. 3 times 3 will be 9. And then remember, with squaring binomials, you're going to get this plus 6i plus another 6i, so you're going to get plus 12i. And then 2i times 2i is plus 4i squared. Now remember, standard form should not have any I to a power higher than 1 in it. So remember that plus 4i squared is like saying 4 times negative 1, because I squared is negative 1. So we really have 9 minus 4, which is 5, plus 12i. That's our standard form, simplified answer for squaring 3 plus 2i. Okay, so here's our first example of a higher power of I. We have I to the 10th. Now, we've expanded I to the first 4 powers. If you keep going with this, I to the 5th, for example, I to the 5th is like I times I to the 4th, or I times positive 1. So when we do this, there's definitely a pattern going on with the powers of I. They repeat every 4 exponents. So let me just write some of these out. I is I squared is negative 1, I cubed is negative I to the 4th is positive 1, and then like I said, this repeats so that I to the 5th, if you actually do some of the legwork behind it, you could say I to the 5th is I to the 4th times I, 1 times I is I. Basically, if you see an I to the 5th, that simplifies down just to I. If you see an I to the 6th, that's going to simplify to negative 1. Why? You could say it's I to the 4th times I squared. 1 times negative 1, negative 1. So you can just follow this pattern. You don't really have to, follow the pattern correctly. I to the 7th is equal to negative I. You don't have to break it down every time, but I always go back to I to the 4th because it's equal to 1. So if you did want to kind of prove to yourself or check your work, I to the 7th is I to the 4th times I to the 3rd, 1 times negative I, negative I. So this pattern will keep repeating. I to the 8th will be the same as I to the 4th, which is equal to 1. Now taking this out to 10 is not bad, so I might as well do it. I to the 9th is I to the 10th falls in line with the I squareds, so it's negative 1. So this answer, I to the 10th, is really just the same as I squared. It's negative 1. What's the rule here? Because what if this was I to the 1 millionth? Am I going to write out this pattern of 4 until I get to a million? Hopefully not. That would be time consuming. Your answers for powers of I are either going to simplify down to I, negative 1, negative I, or 1. So you've got a 1 in 4 shot if you're just trying to guess. But if you want to do this without having to write out the pattern, because the pattern repeats every 4, you could say, what is 10 divided by 4? So 4 goes into 10 twice, and we don't normally write this, right? But you'd have a remainder of 2, right? Because 4 times 2 gets me to 8, and then I need this plus extra 2 to get to 10. What that means is I to the 10th falls into the second column of powers of I, and then the R2, the remainder, tells you which line it falls on. It's the same as I squared. More formally, what you're doing is saying I to the 10th is the same as I to the 4th raised to the second power, and then multiplied by an extra I squared. So check the math on that. Is that right? I to the 10th is I to the 8th times I squared. Yes. I to the 4th is just 1. Squared is still 1. Times I squared. So I to the 10th is negative 1. So that's why the division trick works, you're really saying, I'm going to rewrite this power as I to the fourth raised to a power, and then I will multiply in the extra little bit to bump it up to whatever I need it to get to. Shorthand, though, it's just divide your exponent by 4. The remainder is the important part. The remainder is what line you fall into the I squared line. You will only ever have a remainder of 1, 2, or 3. If you get a remainder of 0, it means it's the same as I to the fourth. It's a multiple of 4. Let's do that again for number 4. So I have 5 minus I to the 27th. So we need to do the work of what is 27 divided by 4. So I'm thinking, okay, well, 4 times 6, right, gets me up to 24. But then I have this remainder of 3. Or if you don't like that, I to the 27th, what we're saying is get it as close to 27 as possible. So multiply 4 by 6 to get yourself up to 24. And then multiply in another I to the third. So we have 24 plus 3, that's 27. This is the same as 1 times negative I. So this is 5 minus negative I, which means we have 5 plus I as our final answer. All right. What if we have fractions? The next 3 problems are fractions, and notice that all of them have an I in the denominator. So remember, I is the square root of negative 1. So just like we said we had to rationalize when we had radicals in our denominator, the same thing is true. I need to rationalize this denominator because the I represents a square root. Now, if you just have a monomial, so just a 3i down here, as opposed to a binomial, 2 plus 3i or 3 minus I, to rationalize, you simply multiply by I over I. It does not matter what number is in front of the I. This could be a negative 3, could be a 3,000, whatever. Multiply by I over I, and you'll see why that works. In the numerator, you distribute your I through the binomial, 2i plus 8i squared. The denominator, 3i times I, becomes 3i squared. Your goal when you rationalize is to not have the radical or not have the I in the denominator. And this works because 3i squared is negative 3. And then let's simplify the top. 8i squared is negative 8 plus 2i. Now, when we do imaginary numbers, or I'm sorry, when we're writing complex numbers in standard form, we're supposed to split the real part and the imaginary part. So we're supposed to do the division. Negative 8 divided by negative 3 is 8/3. 2i divided by negative 3 is negative 2/3 I. So this is technically the correct standard form, real part plus imaginary part. If you have a binomial that contains an I in a denominator, like 6 and 7, you're still rationalizing. And in order to rationalize, we have to multiply by the conjugate. The conjugate is a pretty important thing that we're going to use in several different chapters. It's a way to, conjugates multiply nicely. Think difference of squares. X plus 5 times x minus 5, those are conjugates. And they multiply to be x squared minus 25. So if I multiply by the conjugate here, the conjugate of 2 plus 3i is 2 minus 3i. So a conjugate is just changing the sign in the middle. When I multiply these two conjugates in the denominator together, I should be left with no terms containing I left in the final answer. So let's do the multiplication. First, multiply 5, distribute that through 2 minus 3i, so 10 minus 15i. And then when you multiply your conjugates together, 2 times 2 is 4. You're going to get minus 6i plus 6i, so those cancel. And then 3i times negative 3i is minus 9i squared. So I said we shouldn't have any I left in our denominator, and we don't, right? Because we have 10 minus 15i, and this becomes 4, this term is plus 9. So we've simplified this to just a real number in the denominator, that's 13. And remember, we're supposed to split it up into standard form, so 10 over 13, and then minus 15 over 13i. The i's, either put the 15 up, either put the I up with the 15, or make sure it looks like it's being multiplied out to the side. Like, you wouldn't want to put it down here. That's not true. That's not correct. Okay. So that's our answer for that one. And same thing for number 7, just a different expression. So it's the I in the denominator that's the problem. So we multiply by the conjugate of 3 minus I. If the conjugate is 3 plus I, again, you just change the sign in the middle. And here we have lots of distributing to do, lots of foiling, if that helps you remember. So 1 times 3 is 3. 1 times I is plus I. 5i times 3 is plus 15i. 5i times I is plus 5i squared. The conjugates, we get 3 times 3 is 9. We get plus 3i minus 3i. I don't write that. I didn't write that in the last problem, but you can if you want to. Plus 3i minus 3i. And then negative I times I is minus I squared. With conjugates, it's always going to be something minus something squared. And then that's always going to change to minus something squared is always going to change to plus whatever. So we have 3 plus 5i squared. So 3 minus 5 is negative 2. I plus 15i is plus 16i. 9 plus 1 is 10 in the denominator. So negative 2 tenths plus 16 tenths I. And reduce that. Negative 2 tenths is negative 1/5 plus 8/5 I. All right. Last example in this section is just another higher power of I. So again, for I equals 6, or for I to the 60th, I do not want to write out that pattern of 4 until I finally get to 60. I would rather just say, what is 60 divided by 4? And if you're having trouble with that, well, first of all, you can set any of these up with long division, remember. We just did long division, right? So 40 goes into 60. 4 goes into 6 once. 4 goes into 25 times, so the answer is 15. Or remember, if you're dividing by 4, sometimes it's easier to divide by 2 and then divide by 2 again. 60 divided by 2 is 30, divided by 2 again, 15. What we're saying is I to the 60th is the same as I to the 4th, raised to the 15th power. And we don't need to multiply any extra I in here because we already have 60. And so that's just 1 to the 15th, which is 1. The only other thing we can do with complex numbers is look at them in their radical form and then use them to solve some quadratics. So simplify each radical expression. The rules here, they're basically 2 rules. The first thing, if you see a negative radical, the first thing is to rewrite in terms of I. And then after that you just do the math. So whatever, I mean, I don't have, like, depending on the problem, it's different. So I'm just going to say do math. Meaning like multiply or add or square or whatever. You need to rewrite in terms of I first, because if you don't, you might have a positive answer where your answer should be negative or something like that. So first we're going to start with, if we can simplify the radicals, we should. So we're going to start with square root of negative 27. That is the same as I radical 27 times I radical 15. So first off, there's that. And maybe I'll put parentheses around here. Now radical 27 simplifies, so if you'd like to take it further, I would write it like this: 3I radical 3 times I radical 15. And then from there, you multiply, just like with real numbers, multiply the numbers on the outside. So 3I times I is 3I squared. Radical 3 times radical 15 is radical 45. 3I squared is negative 3. Radical 45 simplifies to 3 radical 5. So my answer is negative 9 radical 5. You want to avoid multiplying large numbers together. I would not do 27 times 15 and then try to figure out what perfect square, which it would be, 81 times 5 is what goes into 27 times 15. So simplify if you can. If you can't simplify, if this would have been like, oh, I don't know, the square root of 30 times the square root of 15, so no perfect squares to pull out of either, then remember you can break them down into like 27 is 3 to the third, 15 is 3 times 5, and you can kind of see like if you're taking the square root of this, 3 to the fourth times 5, what can I pull out? I can pull out a 3 squared, and I would leave the 5 underneath. So that's another way to work with numbers that you can't simplify right off the bat. Okay, number 10. Before we start squaring, we need to rewrite this as negative 1 plus I radical 2, the quantity squared. Remember, squaring a binomial means that you're multiplying it by itself. So if it helps you, write it out like this, or use the trick for squaring binomials. It's the first number times itself, which is 1. Then you're going to get minus I radical 2 minus another I radical 2, so that's minus 2 I radical 2's. And then I radical 2 times itself is plus I squared times 2. I squared times 2 is really just minus 2. So 1 minus 2 is negative 1 minus 2I radical 2. Our textbook might write this, by the way, as minus I 2 radical 2. No, sorry, as negative 1 minus 2 radical 2, and then they put the I out here. Sometimes that looks weird, especially when it's typed up, because I can put a big space like that, but sometimes it looks like the I is underneath the square root. I won't be asking you about the square root of I. So if you ever see that in our bookwork, the I is not underneath the square root. For adding radical expressions together, remember we can only add radicals if they are the same radical, and then we're just combining how many there are. So follow the same rule first. Simplify the I. So radical 12 becomes 2I radical 3. And radical negative 27 becomes 3I radical 3. So really we have 4I radical 3 plus 12I radical 3. And because these are both radical 3's, we can combine their coefficients in front. So 4I plus 12I is 16I radical 3. And again, technically it should be like 16 radical 3I, real part than imaginary part. But I just write it like this so it's more clear that the I is not underneath the square root. All right, so far when we've been solving polynomials and quadratics, we have not had any imaginary solutions, or if we did, we might have just said like not real. So now we're going to go ahead and solve. If I have something I can use the square root method on, like this, x squared plus 4 equals 0, I just have to remember that when I square root both sides, when you introduce the square root, you need a plus or minus, and then the square root of negative 4 simplifies into plus or minus 2i. So those are the zeros of the function. This graph, again, would not be crossing through the x-axis. So when your only solutions for x are imaginary, that's an indication that there are no x-intercepts if you were to graph the thing. For number 13, remember you can't start factoring or anything if this is not equal to 0, because there are an infinite number of answers for like what combinations of x can I multiply together to get negative 5. So first, always set your quadratic or your polynomial equal to 0 before you start solving it. If it has 3 terms, I should say. I didn't do that in number 12. I can't factor this one because you might be saying like, oh, 3x and x, if I put 5 here and 1 here, I can get negative 2, x in the middle. But remember, you're supposed to multiply to positive 5, and this multiplies to negative 5, so that doesn't work. All right, so we hop over to quadratic formula. Opposite of b, plus or minus, square root of b squared, minus 4 times a times c, all over 2 times a. Again, I know that most of you probably have the calculator program that just does this for you. You just tell it what a, b, and c is. But ever since everybody has had that, the number of mistakes I see with just this calculation is kind of staggering. So please practice this without your calculator. 4 times 3 is 12. 12 times 5 is 60. And this is minus. So minus 60. 4 minus 60 is the square root of negative 56. We need to simplify that. So let's see, 4 goes into 56 14 times. So now I can make this 2 plus or minus 2i, radical 14 over 6. And again, if you technically want to put this in correct standard form, you need to separate it out. 2 over 6 is 1/3, plus or minus 2i over 6 is I radical 14 over 3. But if you said 2, 2, and 6 are all divisible by 2, I'm going to accept either answer. The AP exam is going to accept either answer. I would imagine you would just be expected to know that these are equivalent if you're looking in a multiple choice answer. They'll probably write their answers like this, standard form. Okay, that's it for today. Make sure you come to office hours if you have any questions about today's notes.